very hard to start now to talk about the however, I want to talk about the spin receptors. There are some limitations to it, also in the manufacturing and also the sensitivity and how with it. First of all, I'm from the Austrian Institute of Technology, so we have different places. I'm located in Vienna. There we also have student building and student research group here. We are a non-university research center, and so we act as a bridge between politics, industry, and science. I'm working at the center here, Biosciences Center, and including a field of molecular diagnostics. Here we have different fields we work in. So it's not only biosensors, it's also biomarker discovery, mainly cancer biomarker discovery, critical barriers, assay development, system integration, bioinformatics, and also the biosensors, all with the aim to realize a point of care test system. And I work in the biosensor fields where we develop magnetic sensors, electrochemical sensors, and this part of this unit is led by Hainberger. My specialty is surface modification of the sensors. You know, every surface has some special things you have to address to get the system run on it. And to the topic of biosensors, especially amperometric sensors, you know, there's a huge history behind it. It starts very early with the oxygen detection on a blood electrode and goes then on with the detection of glucose, different enzyme reaction. Also, immunosensor, we use enzymatic reaction to make the sensor running. Then comes the DNA sensors. And also the nanomaterial comes more and more into play, but never reached the mass market in this big than it could be because of the nanomaterial fabrication issues. And then what's very important also in flexible printing electronics comes to variables. There's not too much time here also to present the work we do in AT or in calculated variables, but it's a very interesting and very exciting field where we have a lot of system. At the AIT, we work mainly on sprinting biometric sensors, and we want to do more than one parameter. So we set on an array, which can become bigger and bigger. At the moment, we are at 12 parameters. We can detect how it's the discussion like at 16 or 32 parameters. But this is important to address the need in the technological fields to detect the parameters in more complex solutions or more complex questions. We also support the customers by making devices. We talk about amperometric sensors, and I just want to give you an understanding. We can do different methods with it. So one method is the Thöny amperometry. So you apply on your electrode system, which is here, so you have always reference electrode, counter electrode, and working electrodes, and apply a potential on the working electrode, and then you measure the current. So it's the simplest case, the best case to monitor, for example, enzymatic reaction. Then you can make different Schalkhammer voltammetry. Here you make your protocol, how you change the potential, then the end of the peak current, and then you can measure the peak current from the redox to the compound. And the next simplest way to make an amperometric sensing possible is the cyclic voltammetry. We change the potential from minus to positive back again, and then if we have a redox active compound which enables it to get an oxidation and reduction peak. This is again functional to integration of redox material solution. And for the redox materials, there are billions of different compounds you can detect, also natural occurring materials. And here are just a few of them, but I just want to show you the complexity on the example of them. So we have some complexes which are very interesting sensing properties, and we also have organic materials which comes as a product from enzymatic reaction. All of these materials have to approach very close to the sensor surface that this redox reaction is happening. So it has to fit together in the polarity, but also in the structure. When you have a double bound system, then you also have to guarantee that this system can the active pure sensors. And to make it more clear what this means with printed electronics, I'm just bringing a simple example from our research. It's done in the NACUS project and the Pioneer project part. So we have an actual sensor, raw material, which is a very fine structured graphite materials, and we have a dropset sensor, which is another kind of graphite. And in a special case, we want to detect this NLH. We have here a very big difference in sensitivity regarding this redox. And so is the question why this is happening. The whole goal should be graphite, but truly one contains a binder, as we find out when we make this plasma treatment on it. It's a very common method. You see, okay, you use all this binder material, and it's very strong and changes the sensing behavior on your material. This is on two aspects bad. One aspect is when you can do oxygen plasma, moving a layer, then this material is very prone to oxidation. And you want to store this material under normal conditions, then it will also degrade by time. This is maybe also why it's worse before, because they are just degraded. The second material survives this plasma material is very interesting, and also electrochemical sensing properties quite similar. So we are decided for this material to ensure sensitivity. And use then sensors select for detecting of beta bodies, and beta bodies are produced when we don't be able to use glucose or energy supply in the body. When you, for example, take a diabetes patient, or you are so sporty, then you don't eat something before, then you also produce ketobodies, for example. But when these ketobodies are produced too much, then you come to a critical disease conditions called good ketoacidosis. And then you feel blurry, stomach hurts, and so on. And so there is no balance. And then you have to detect this one, these two ketobodies, to understand what's happening in the body. Currently, in the normal ketobody detection systems, you just detect one of them, but also makes sense to detect the ratio, detect both of them. And this is what we based the study to understand if we can detect both ketobodies in the sensor. And therefore, the companies here, we go for the sensor, which is based on a recycled paper substrate, and then developed a simple assay based on an enzyme that redoxybutyrate dehydrogenase, which can convert the acetate or the redoxybutyrate in different stages by either consuming or producing NADH, and this is what we can measure. So we do another sensor, just put that in a reaction mixture, measure this initial current, and then we add our sample, wait 5 minutes, make the next measurement, and what we get then, difference of both currents, absolute to value, we get similar behavior in the integration curve, both in this range. Now I want to give you another example. So when you want to detect, you can detect directly this reduction on the surface or in the interaction with the biome. And one very famous idea is around is when you have Affiliation structures, a DNA structure with negative loaded and a positive loaded complex. And when the target protein of interest comes, it just replaces then this redox molecule, and so the redox molecule has a higher mobility we can measure. And this principle, we look at this project Bacchus, which is called one of the detection, where we want to detect the DNA and protein as markers for RNA. And to do this composite here, we have support by the Schalkhammer University, which starts very basic with a application of phenoxide, who then gold particle solutions and step together, according to also we get also nanoparticle composites. Then we characterize this composite, and most important is here that we have here the phenoxide lake, where the single sheet phenotype decorate voltage. So nanometers. For sensing, we modify this composite aptamer and then formulate an interpret and then place it on the sensor. Sensor. And here you see some test lines of this material and also to control to see that this material is intact after printing. We make again IFM. So the still bakes, so it's more copying of the space of the print. And what we want to know then is how the sensing changes, and here's the big disadvantages of cyclic photometry. So if you change something on the surface, bring load into it, you also get the higher capacity current. This is what we also see. However, when we put this composite on the sensor, you see that we can still measure our analyte, which is hexamine. Very interesting fun fact is to get back here and have done some sheet, which is we can see the single sheet and also some this highlighted dots. There are this gold buttons. For the assay, we go then for different sound files ultimately to get rid of this capacity currents and have then the sensor prepared our aptamer called amperometric composite and solution on it, which carries down the very specific compound, and then add some protein at different concentrations and make measurements. And so the ruthenium is free, so we get an increase of our. Yeah, and so we can do this from the combine and find here. Another thing what you can do on the sensors is using an enzyme as a label or as similar to a sense label to detect the biomolecule. So here you see the construction of DNA, capture DNA, binding DNA, and then we have the biotin, this linker, bridging molecule as a structure reading, and then we have HOB, phosphatase peroxidase, which converts this TMB into box. And this substance issued an electrons for the sensor. And this sensing was then implemented in project Predict. We detect circulating tumor DNA as a biomarker of biopsy. And here is important to have one hand fast diagnostics of patients, and on the other hand, for early diagnostics and also for support. So we want to know which patients this patient had, that we can give the right treatment. Generally, we have to say that this circulating tumor DNA, what we want to detect is in the bloodstream, and this part of all is circulated DNA. It's so beautiful shown here with some very structured DNA, but it's not the case. In the blood, we will have different kinds of compartments, different lengths, different hybridization states. So it's a big mess. So don't think that this is a structure. And this is a big problem later for a patient. And what you have to do to analyze this DNA is, first of all, you have to extract it. And you need at least 5 ml blood count concentration, which you can start when the bleeds start. So also for early diagnostics, you need also this extraction. Then we focus here on breast cancer. So we focus here on field-wide mutations, which have 36% prevalence in breast cancer. These markers are FDA approved, and they can also be used for if advice treatment of cancer. Normally, it is normal PCR detection systems. We take a sample which is purified in blood, and then like with microplate all on the liver. Then you have the preview plate, washing procedures, and so on. So we take about 1 day. So what we have, the idea is again going to find a care system, easier for us to on. But in this project, we just started with understand what would be the steps to realize in such an assay, which is maybe then quite complicated. And therefore, first we have to understand how this patient specificity works. So we start with a microarray and designing the capture probes with specific place where the patient is, all the three capture probes, and also the A length, which also should contain a certain position, location, so that fits together. But what you also do is also make a printing buffer to enable the best application of the sensor microarray first, and then transfer all the protocol on the sensor, which is also a gold-plated sensor. And so what we see on the patient specificity, so it's similar from the microarray to the sensor, and this is a big progress. Also, if it's not seen in this way, because when you're starting from having first microarray, you can detect 1 billion different biomarkers at the same time, you identify the interesting biomarker, and then transfer it to the sensor to then have a win here. But as I mentioned before, it's very critical the length of the DNA you want to detect. Because here comes interesting thing today, that most of the publications do analyzing fine mutations just using short DNA. But this, as I said before, it's not present in the blood. So in the blood you have different ones and they're all bigger than 100 base pairs. And when you then look here, you could not control how this interaction is, how is this overlapping end of the DNA, the surface or outside. And you always have some repulsive forces. And this leads then, when you have the long DNA and the former DNA, and even in the best condition, you see that the long DNA has much worse limit of detection than the short one. And this also affects you then the mutation specificity you want to reach. So also for your mutation specificity, long DNAs are very critical. But this action principle is also bring us back to the surface and what the sensor is made of, because here you also have again a big variety of different materials. And recently we can show that the different varieties of material make a big impact on the patient specificity what you can do. And here we get this big variation of different materials from Attophotonics, but here is a gold sensor. Let's get gold sensor on silver. Here we have gold particles modified on silver, silver, even more gold particles, and so on. In fact, what we find is that this gold particle modification leads to the specific morphological structure, which then enables us to have best specific for the fine mutations. And this we can see in this picture here. I know it's a lot of data, but this is the discrimination factor of all three sequences I named before on all the different materials. And here we see that this gold particle has the best integration, and this we can also show here again. So what we have take home message with our morphology and our certification played an also big role on the separation of these populations. And as the story not ended, because what I tell you before, all the signal length, there is a big role, and therefore we need isotomal amplification. On the first hand, it's because we are not sensitive enough to detect direct. On the other hand, we also have to guarantee that we always have the same sequence length, and therefore we use isotomal amplification. And therefore, we developed a system which leads us to a single strength DNA which enables us then to have the best stabilization conditions to separate the mutated DNA, the non-mutated DNA, in the localization of the capture surface. Second thing, what's interesting here, but not realized too far, is that in this Schalkhammer application, we can also knock out the non-mutated DNA by implementing we have to do for the very high, we have also purified our single strain DNA. And to do so, we can put them on the sensor surface and apply detection, and also range, very good notation specificity and separation. And next to the enzymes, there's another very interesting thing, which some of the partners of the predictive project, which is there is they fabricate Autsrian particle on a complete-based core. They give an gold platinum alloy, and this gold platinum alloy enables to sense DNA similar to the enzyme, but due to this mechanism here, it's even possible to sense for higher sensitivity. So they use sensitivities which are also coming close to the range. However, there is some issues to this nanomaterials to the press also the usability propagation. And they also do it with the short mRNA, which is still some problems. In summary, the big project was that we have a microarray where we can do different assays, and then bring the optimized assay to the sensor. We can do enzymatic assays with picomolar range, nanomolar range, depends on the sequence length measure. And for this nanoparticle approach, markers can also show that there are very well detection limits. The Eisenhower application is was still necessary to go for this enzymatic approach, reach the sensitivity, but also reach one size of the DNA. And with this approach, reach the long range, which is a good start for detecting microorganisms. However, nanomaterials become more and more important in the future and will also be with a little bit of game changer. However, there are a lot of problems during. One is batch-to-batch migration, which is not really for this very exciting materials, not perfect. And we have also the problems that the ligand shells around this particle are always different, and the ligand shell also have a big impact on the catalytic activity of this material. And for producing the sensors which are enough to make fixed biological studies, we need also high volume production methods. And in fact, we will also process them, so we should also find the right processing. So thank you very much. This is the team of the big project. I just a special thanks to Vanessa Thöny, who makes the PhD of this project, and who was a lot of the work of this DNA mutation-specific assays. Also much thanks to our diagnostics team. So we have different fields, and also this helped us to understand one another critical question. So thank you very much for your attention.